Based on what we have from the previous lecture, Ajahn has mentioned about the new method that we are learning. This one is one of the powerful methods developed by a professor at University of Illinois in the United States. Okay, it is a kind of displacement method. That means it's going to use the displacement as the unknown. What the displacement? Displacement is a kind of deformation. Deformation is a bigger one than the displacement. Deformation is the shape of structure change. The displacement is the location change. And what we are studying the structure that's built, by steel. So the course that you are taking next is going to be the steel design. The reinforced concrete design, that is also another course. And also the pre-stressed concrete. All of this material is called the deformable material. When the deformable material subjected to forces. Remember where the forces come from? Oh, Ajahn, we didn't call it forces, we call it load. Yeah, we can call it load. The load comes from the weight of the structure, such as the dead load. Or if you guys go to the Facebook, I just put the important life load that occur in the United States is the force of the hurricane. Another one is the life load. Life load change the shape, the magnitude with the time. But most of the dead loads still there without changing with the time. So for example, the weight of the reinforced concrete beam also. When you analyze the structure, Ajahn will provide you the structure with the loading and remind you again, you're going to go to two things. Okay, one is going to be the building code. That is going to be the legal stuff. You got to follow this code. And most of the life load and the dead load come from the building code. However, the design code that you use in the design of the steel from the EIT, Engineering Institute of Thailand, or for the ACI, American Concrete Institute, or Pre-Stressed Concrete Institute, they're going to provide you the design code. However, the design code going to give you the load combination that you're gonna follow that, okay? And also, basis upon this, under the application of the load, we have the assumption. The assumption is the material will be have in the linear elastic manner, and also with the small deformation, and then you go back and you recall it's going to be very small because you said the Vmax is going to be less than L over 240 if the wall have if the beam have no wall under it, or if the beam have wall under it, it's going to be L over 360, for example. And that is going to corresponding to the linear elastic. And then we come to the method of slope deflection. We're going to analyze the structure based on the displacement as the unknown, for example. Okay, you have the beam, and then your beam, for example, fixed over here and has the roller over here and subjected to the force over here. Under the application of the force, you may imagine that the deformable body will move. For example, for this one, the position of this C will move to this C part, but the position B is still there. The position A is still there because B is lower and A is fixed. So the structure start to change the shape. So this one supposed to be the shape of the structure, and it's going to concave downward. Since this one is fixed, so the theta sub A is 0, the delta sub A also be 0. So over here, the curve must change the shape to concave upward. Okay, and then you get this one as the inflection point. It's going to be the inflection point. And what you have over here is called the displacement. This is going to be the delta sub c. And if you measure the rotation of the tangential line with respect to the horizontal line, that is going to be theta sub c. Okay, and also if you notice at the B, okay, at B, the delta sub B is 0 because it's the roller. However, if you measure the rotation of the tangential line over here, it's going to have the slope, and the slope here is going to be theta sub B. So what we have now, the theta sub B, okay, the theta sub C. Can I change the color of this over here? No, just move this a little bit. Okay, theta sub B and theta sub C, and also the delta sub C. All of this is going to be the unknown, okay, for the displacement method and for the slope deflection method. Now you got these two theta as the slope, and you got the delta sub c is the deflection. Now you start to understand the first learning objective. Understand the concept of the slope deflection method, in which the slope and the deflection, they call the displacement, they are the unknown. Okay, and then we will provide you with the design equation. Based upon this, you're going to analyze the structure. Okay, and then you will have the member that you consider as the AB and the member BC. Okay, by using the slope deflection method from the previous lecture, we have the equation for the moment occur over here. We call it M sub AB. Okay, and then this one we'll call M sub BA. And also you may consider this one is going to be clockwise direction, M sub BC. And the last one over here is going to be M sub CB. By this one, you know M sub CB is 0. But anyway, you have the slope deflection equation. And the slope deflection equation can separate into two groups. One is going to call the general form. Another one is going to call the special form. Okay, another one is going to call the special form. The general form, let me just like it. Okay, if you're talking about M sub AB, M sub AB will be equal to 2EI over L. What EI? EI is the stiffness of this member. And what is L? The L is the length, okay, of the structural member that you are looking for. For the E of the steel is going to be 200 gigapascal. And for the I depend on the section is maybe BH cubed over 12 if you have the section with B and then H. Okay, you know that already. And it's maybe in the unit of, for example, 110 power 6 millimeter power 4, or we may call it to be 110 minus 6 meter power 4. And that's going to put it over here. And then the slope over here is theta, so it's going to have 2 theta. And the slope at another end over here is B plus theta B. And somehow the structure have the downward settlement called the delta, so minus 3 delta over L. And then it's going to plus the fixed end moment due to the applied force. But for this one, the applied force is 0. The fixed end moment going to be 0. And also you have M sub BA. That is going to be 2EI over L times 2 theta B. Since B is the leader, okay, 2 theta B plus theta A and minus 3 again, delta over L. And then plus fixed end moment BA. That is going to be the fixed end moment corresponding to this section. And based upon this, what you consider? The moment that you are consider over here can be considered based on the deformation theta sub A. The deformation theta sub B. Okay, theta sub A is here, theta sub B is here. And the downward settlement over here. And also this one for the external load. Okay, that's we just mentioned about over here. Okay, so this equation will be used for the computation of the unknown deformation and of the this called, what is this called? This called again terminology called it end moment. Is the moment at the end of the structural member. Okay, and for the spatial form, that is used when the structure have some kind of spatial form, such as this one. Okay, you have the beam, and then you have this one as, let's say, this one is a fixed, this one as a roller, and this one as a roller. By putting the force something like this, okay, you may consider from the previous discussion over here, okay, if this is A, this is B, this is C. Again, let me mention it again. This portion, this segment, let's say this segment AB, okay, will have the equation of M sub AB and M sub BA. However, for the BC, the BC is different. The BC has the roller, okay, the roller, what's so-called the external roller. Since this is the external roller, what we have is the moment that occur in this member. Okay, again, it's very similar to this. It's going to be M sub, again, clockwise, M sub BC. And this one is going to be M sub CB. And M sub CB here is 0. Okay, by using this one, okay, and putting into this kind of form, the member here will have only M sub BC that you can compute from 3EI over L. And then it's going to have the theta over here, only theta sub B minus delta over L. And then it's going to involve with the fixed end. It's going to be different from this fixed end. This fixed end will come from when both sides of the member is fixed, but this one will come from the fixed end when only one side is fixed, another one is the lower. It's going to call fixed end moment BC. Okay, we did talking about these two equations, and I also asked you guys to go back and trying to remember this. Okay, next, coming to the step. Okay, that we're going to use in the computation of this. So the first one, after you analyze the structure, for example, this one going to be the unknown, theta B, theta C, delta C. Okay, and if you follow this one, you will get this one, theta sub A is 0, delta sub A is 0. And if you consider this one will have theta sub B, and delta sub B, let's say, it can be 0, or it also can be set as the settlement. Let's see, if we set this one as a settlement, this theta sub B have the delta settlement. This is going to be the known. The settlement is the natural occur due to the foundation moving. Okay, review is will be known. Okay, and then what we have is this one is going to have the zeta sub c, and the delta sub c is 0. If you analyze this one, you will see this one will have this one as the unknown, and this one has the unknown. If you keep using this one, these two one, you will have the moment of this one is going to be m sub ab, and this one going to be m sub ba. And for this one, if you use the general equation, you will have this one for m sub cd, and this one for m sub c. This one going to be bc, and this one going to cb. If you use the general equation, this problem will write 4 equation of slope deflection equation. Okay, but again, if you use the spatial equation, you will have this one for m sub a b. You will have this one for m sub ba. But for this member, you will have only this m sub bc. And basis upon this, you cannot obtain the zeta sub c. I should mention about this and be careful on this. If you not understand this, please review this video clip. Okay. So the problem is going to depend on the shape of it. And now, let me move. So after you specify, for example, zeta sub b and zeta sub c as the unknown, you're going to start by this is an unknown. Sorry for a bad writing. Let me erase all of this and write it again. It's going to be unknown. It's going to be unknown. Okay. By considering, and then you consider to determine both. Okay, zeta sub b and c. That means you're going to first, you're going to find the fixed end moment, because basis on this equation, this is the one that you know. Zeta sub a you don't know, zeta sub b you don't know, but fixed end moment ab you know. Okay, so basis upon this, let me erase this area a little bit, and then let me draw the inference line. Okay, for this one. Okay, and for this one, I will start by consider this portion. Since I use the general form of equation, this is going to be fixed. This is going to be fixed. Let this is going to be 10 kilonewton. This is going to be, let's say, 2 meter, and this is 2 meter. You may find the fixed end moment over here from the table that has in the books, okay, or some of that in the table. You must remember that for this one, you will have the fixed end moment, and this one going to be fixed end moment AB. And since this beam portion is symmetry, this F sub baby will be equal to fixed end moment BA, and it's going to be determined from PL over, if I may be correct, it's going to be PL over F. Okay, that means you will find a fixed end moment. And also for this one, you may find another one of this. Let's say you have the same load over here, and that means you're going to have fixed end moment on these two. That is going to be fixed end moment. This is going to be CB, and this is going to be fixed end moment BC. Okay, and they all are going to be equal. That means you're going to determine fixed end moment. Okay, but if you come to this set of equation For the option, you won't get the zeta sub b, and then you're going to use another set of the fixed end moment. So I left this to talking about it later. So this one will talking about it later. And then second, after you find a fixed end moment, now you come over here. You can write the equation of slope deflection. Okay, now you will have the total of the flexion. You have two members, right? You have 4 of them. So you're going to get M sub AB, M sub AB, and M sub BA in accordance with the fixed end moment, let the bull. And then you also can write the author M sub BC, M sub BC, and M sub CB. This will be in the form of equation related to this. And third, you may come to this portion again. And then on this one, you have the moment act on the structure, and the structure must be in equilibrium. So next one, you're going to write the right equation of equilibrium to find the unknown. Okay, the equilibrium to find the unknown. Let me put it over here. That is going to be the point A over here, and this is going to be the point B, and this is going to be the point C, and then M sub AB will X over here. This is going to be M sub AB based on the third law of Newton. And then you will have this one as M sub BA. Okay. And you will have this one for the M sub BC. Okay. And then you have another one as point C. M sub CB is going to be over here, M sub CB. Now, you have two unknowns. You require to have two equations of equilibrium. One is going to be the equation of B. Another one is going to be the equation of equilibrium of C, because you're looking for zeta sub C, so summation of the moment about B equal to 0 and summation of the moment about C equal to 0. This one you will get M sub BA plus M sub BC and then equal to 0. And another one over here you will get M sub CB equal to 0. And then later 1, 2, this is T. You saw, okay, you saw for zeta sub B and zeta sub C. And then the fourth, you find what's so-called the end moment over here. So find the end moment by what? By substituting this one back into this equation. So you will get the value of M sub AB, M sub BA, M sub BC, and M sub CB. And finally, this is going to be the number 5. You can use this end moment to draw free body diagram and shear diagram and moment diagram and elastic curve, okay, whatsoever, etc. Okay, and that is what we has, okay, for what we has for the slope deflection in one page. Now go back to the example. So sorry, go back to the homework. You have 3 homework. By this 3 homework, you got to solve it, and then you got to compare the result from the manual calculation from the substructure program. Okay, and then let me just recall it. The displacement method. Okay, from the previous one, we use zeta sub B and zeta sub C as the unknown displacement. Technically, we call this one the degree of freedom. this is going to be the degree of freedom, is going to be the unknown displacement for the slope deflection method. And then you get the fixed end moment, and then you write the slope deflection equation. Okay, then if you remember what you have, the slope deflection equation is a kind of force displacement relationship. The equation that I just give you over here, okay, if you try to think it deeply, these two equations is a kind of moment and slope, okay, that is a kind of force displacement very similar to this, okay, and then you use the equation of equilibrium, okay, you use the equation, the above over here, that is going to be the required equation of equilibrium to solve for theta sub b and solve for theta sub c. And then you just plug this one back into this one. So you will get the value of the end moment. Okay, m sub AB, m sub BA, m sub BC, m sub CB whatsoever. And then later you use this one to draw the shear moment diagram. Okay, and then again, the limitation, the material we have linear, elastic under applied load and small deformation. And I should mention the deformation only occur due to the bending. Okay, there is no deformation due to shear and due to the axial force. So there is no axial deformation for this slope deflection method. Okay, and let me go a little bit further. Go back to review what we have. Some of you guys must use this knowledge to take the entry examination for the Council of Engineers of Thailand. Okay, first we talk about the degree of indeterminacy. Okay, determinacy is defined as the total unknown reaction or internal forces and the moment, and minus the number of equation of equilibrium. If we do consider the axial deformation and axial load, for example, for this one, under application force, the reaction going to be 1, 2, 3, and then going to be 4, 5, 6, okay, and then 7. We have this one, the total of 7 unknown. And if you know the free body diagram of the beam ABC, you will have 3 equations of equilibrium. So this structure, this beam, going to have 4 degrees of indeterminacy. Okay, it's going to have what? 4 unknown redundant. Okay, so it's required 4 redundant to solve this problem. How about this one? This one will have 1, 2, 3, and then 4. This is 4 unknown reaction, and you have 3 equations of equilibrium. So this one requires only 1 redundant. So if you use the knowledge of consistent deformation, okay, this problem will solve easily. But this problem will require a lot of work, okay, to solve for 4 unknown. Okay, this kind of analysis of degree of indeterminacy can be found in the metric displacement method. Okay, for somehow you may not consider the axial force in the beam. If the beam not subjected to this kind of axial force, if this kind of axial force is 0, so the summation of x sub x is 0. The number of equation of equilibrium reduced from here to 2. Now you have only 2. You have only 2 for one free body diagram, right? So the unknown, this one going to be 1, and 2, no axial deformation, 3 and 4, and this one is 5. So this structure require you to have T redundant. So it's still not that easy, okay? You still need a lot of work. And for this one is going to be 1 and 2 and 3. So it's going to have 1 degree of indeterminacy again. By considering this is only 1 redundant, right? So it's going to be easy to solve by the consistent deformation. I will show you later this kind of beam that has a number of support, okay, has high degree of indeterminacy. This kind of structure can solve by the displacement method easily, okay? But in the opposite direction, this kind of structure that has less support, it can use the force method to soak it easily. By doing that conclusion, we're going to consider another thing. Okay, we're going to consider the degree of freedom, but before consider the degree of freedom, you got to know about the node. Node is any point on the structure that you are looking for the unknown displacement. For this one, we come back to the concept of elastic curve. For the concept of elastic curve, this is going to be fixed. This is called the node. This is going to be fixed end. And this is going to be the roller. Okay, this is going to be fixed. And this is going to be fixed. Under the application of the force, since this one is fixed, so theta sub A is 0. Delta sub A equal to 0. So the displacement at node A is 0. And then you may bring the ruler. And if you put the force, okay, you push this one, the force, and then you hold the point A and point B fixed. So you get the deformation somewhere like this. So under this, the elastic curve of this portion will have concave downward. And then if you come to another point over here, this also has theta sub C equal to 0, delta sub C equals to 0, and then it's going to concave downward. Okay, and at the middle, okay, at the middle, it's going to have concave upward like this. So by considering this one will concave upward, and later this one will need to join together. Sorry for this. Okay, let me erase this one for bad drawing, and then you will have this one as the deformation. Okay, so what about this one? You will have theta sub B over here. If you draw a line in the horizontal, this line horizontal will change to this line. Okay, and then you have the rotation like this. This is going to be the clockwise rotation called theta sub B. The clockwise rotation is positive. And how about the delta sub B? Delta sub B is 0. By considering the node at A, B, C, which is the support and the joint, you will have the theta sub B for this problem as the unknown, only one unknown. So if you use displacement method, okay, to solve this problem, you only have one unknown. That's what I did conclude to you. If the structure has a lot of fixed support, the displacement method is going to be very powerful method to use. Okay, and come to the next one. Okay, not only the support, not only the joint, you also have the free end like this as the node. Okay, Under American force, the 10 kilonewton will move point A here. And then for sure, the beam gonna have some kind of this deformation. And then it's going to have the inflection point here. And then it's going to concave upward. Okay, and then it's going to do the same. Go with the concave downward and link to this point since theta sub c is 0, since delta sub c is 0. And somehow over here, the theta sub b still be the unknown. Okay, zero. Delta sub b is 0. But for this one, if you consider the delta sub a is going to be the unknown. And also if you measure the slope here is going to be the plus, sorry, this is counterclockwise, this is going to be negative, okay, it's going to be negative theta sub a. We have 3 unknown for this one. This one we have 3 degree of freedom as the unknown. This one we may call it just have 1 degree of freedom as the unknown. So if you solve this kind of problem with the displacement method, you're going to require a lot of work. Okay, and compared to the previous one, this kind of structure, as I conclude, you may use the force method, is better. So this conclusion is important, guys, when you take the education exam. So the degree of freedom is a kind of by the definition of slope deflection method, the displacement at the node that you are, okay, you are looking for. Okay, it's just like the unknown displacement. Okay, it's an unknown displacement. Again, from this structure, the wire here under the no force. If there is no force applied to it, it's going to be in the horizontal. But when you put the force like this, the structure will deform and the elastic curve of the structure will be as shown. This is the real thing. This is going to connect your experience, your real experience with the model we just discussed. Okay, let's say if even though all of this is a pin, or you may set this as a pin and roller, okay, it's maybe the pin and maybe it's maybe the roller, because when we analyze the beam, we said no axial deformation, okay, under this consideration. What we have over here, you have this one for theta A. You have this one. If you put this one, you have this one. On the left hand side and on the right hand side, they are going to be theta B equal because the connection is rigid. I just mentioned this previously, or we will have mentioned about that when we're talking about the slope deflection equation. And this is going to be the theta sub c. And the last one over here, this is going to be theta sub d. Based on this, you will have 4 degrees of freedoms. Okay. If you analyze this structure, okay, based on the general slope deflection equation, you will have 4 degrees of freedom. Okay, that means you're going to have this m sub a, b, m sub b, a, m sub b, c, m sub c, b, m sub cd, and m sub dc. But you also have the spatial, okay, spatial equation. Again, for the spatial equation, if you don't want to find the theta sub a and you don't want to find the theta sub d, okay, based on the spatial equation that I mentioned previously, you will find m sub ba. Since the m sub ab is equal to 0, okay, and you find M sub BC, M sub CB, M sub CD, M sub DC is 0. Okay, that means the number of slope deflection that you are writing will be reduced from 6 to only 4. Okay, only 1, 2, 3, and 4, and the unknown will reduce to only zeta sub B and zeta sub C. So depend on what the requirement you are asking for. Who going to set the requirement? In this course, I will, but when you work, it's depend on you. Okay, so it's depend on. So this problem is can be first like this. It can be second like this, and it can be third. It can be the third. On the third, Ajahn may ask you to determine zeta A, zeta B, and zeta C. Okay, this is going to require you to determine only 3. Okay, that's it. And also, fourth type of it, it can be fourth type of it. The fourth type of it, I may ask you to determine zeta B, zeta C, and zeta D. Okay, this is another kind of problem like this. It can be 4 types for the examination problem that you guys may have in the coming future. Okay, if you want to understand it, just stop this video clip and listen to what I'm saying clearly. By first, you got to understand the general form of slope deflection equation that I just mentioned previously. And the second, we got to understand the special form of the slope deflection equation. And then you can separate this problem into 4 types of it. Okay, my teacher said, when the student can make their own examination problem, they are going to understand everything. Okay, so I just like you guys to go back and try to work on your own. Okay. Oh, this beam has total of 4 degrees of freedom, as I just mentioned. But this problem can be classified into the 4 types of problem. Okay, now for the degree of freedom, also separate into 2 types. One, we're talking about if we do consider the axial deformation and axial force, or another one, if we do not. Okay, it will provide the different consideration. Let me come this one first because we will study the slope deflection equation. For the slope deflection equation, there is no axial force and there is no axial deformation. Again, if you go back to the problem that I just mentioned before, this one is fixed. Okay, the deformation of this one will be something similar to this one that I just mentioned. And again, the zeta sub A is 0, the delta sub A is 0, zeta sub C is 0, delta sub C is 0, and delta sub B is 0. Only zeta sub B is going to be the degree of freedom for this problem. And again, this one, okay, we'll have the deformation, something like this, and going to have this kind of deformation. And again, you may have this one for zeta sub C equal to 0, delta sub C equal to 0, delta sub B equal to 0. Now, in this problem, there is no axial deformation. You have zeta sub B, okay? You may have delta sub A, which is going to be the deformation that occur at this vertical, okay? And then you also has this one for the slope of zeta sub A, okay? Like I mentioned over here. Again, Next, later in this part, we will use the metric displacement method to analyze this structure. In the metric displacement method, okay, they said a node will have three deformation, theta, delta sub for a y, delta sub a x. Okay, for this one, okay, theta sub a is 0, delta sub ax is 0, delta sub ay is 0, since it is a fixed support, and theta sub c is 0, delta sub cx is 0, delta sub cy is 0, because it is fixed support. The B is the roller, okay? Since the B is the roller, the B only prevent the deformation in the y direction. That means is the B can deform in the x direction. So it can be theta sub b here as the previously mentioned, and it's going to be delta sub dx. So that is going to be 2 degrees of freedom, okay? And coming to this problem, okay, as I mentioned before, this is fixed, theta sub c is 0, delta sub cx is 0, delta sub cy is 0. The B gonna provide as before here. You're going to have the theta sub b and delta sub bx. You have 2 degrees of freedom here. And since the A here, since it can be deformed, so the deformation of this one will change to something like here. So you will have the vertical deformation. Previously, you have delta sub A y, and you will have this one for the axial deformation, delta sub A x. And finally, you also have the slope over here of theta sub a. So you have the total of 5, okay? But most of the time, we didn't much consider this way. But I must mention about this to cover everything you're supposed to know, okay? Concentrate on this slide, okay, when you take the examination. And when we compute this, we come to the problem. Okay, review again. For this problem that has a lot of support, this one will be so easier when you use the displacement method. Okay, following what I mentioned over here. Okay, but when you come to this kind of problem that has less support, the force method is going to be a better choice, okay, for you to use. The reason is this, okay, I left the word under this slide for you guys to review it again, okay, no matter is do or do not, it's going to provide you the same lesson, okay. For the frame, I should left the frame over here first. Yes, it's okay. Just mention about this, just go along it. But the first one, we're going to base this on this one. This is going to be what you are going to learn for this portion. Again, how about the degree of determinacy? Where this come from? For this rigid frame, what is this frame? Under the application of the force, theta sub A is 0, delta sub AX is 0, delta sub AY is 0. Okay, and also for this one, all of them are 0, all of them are 0, since the support is fixed. Okay, and then what happened is this fixed, right? When it's fixed, it's going to provide you the force. It's going to have this one corresponding the x corresponding to this, the y corresponding to this, and the moment. So when you fix it, you're going to provide you the reactions, the force and the moment. So all of them going to be 9. And if you have only one free body diagram for this frame, you have 3 equations. So this is going to be 6, the total of 6 unknown force. Okay, that is have 6 redundant. Okay, and then coming into this, since this one fixed, so all of this is 0 on the formation here. So there is only the slope occur here, since there is no axial deformation of the beam and axial deformation of the column. And this is going to have only slope zeta sub c. So you have only 2. So by doing this, this is going to be good if you use the displacement method. Okay. Now consider this one. If you come to this one, you have this one as the reaction, this one and reaction, total of 6. And you have three equations per one free body diagram of the whole frame. So you have 3 degrees of indeterminacy. That means for this problem, you require only 3 redundant. I write this one wrong. Okay, this one redundant force and moment. Okay, and how about the degree of freedom? Okay, you still have the zeta sub b and zeta sub c. Since this one has no axial deformation, you will have the delta sub b here. And you may have the slope zeta sub a here. So it's going to have 4. So by doing this, for sure, the force method, okay, going to be good for this kind of problem. Okay, for doing this, if you come to the matrix displacement method that we are going to take it in the second part of this, the analysis is going to be like this. Okay. Coming to this, you're going to have the unknown force of 3, 3, 3, 9. And then the equation is going to be 3. So the same as before, you get this one 6. Okay. But since the beam can deform, so the B under action force is may move like this. So it can be delta sub Bx, it can be delta sub By. It also has zeta sub b. Since the deformation can occur, okay, the same occur as C. That means you're going to have 6. So now, if you use metric displacement method, okay, metric method, the displacement and the force method going to provide the same, okay, the same unknown, okay, of 6. And then if you come to this problem, again, you have the unknown of this one for 3, this one for 3, and then you get 6 minus the number of equation is 3 degrees of indeterminacy. However, if you come to consider the degree of freedom, the degree of freedom as we just talking about, this is going to be 3, this is going to be 3, as just we mentioned. This one also going to have 3. So the total is 9. If you come to this again, the force method, okay, the force method is going to be the better method for this problem. I just mentioned about this because this knowledge is required for you guys to take care of the engineering license, okay? And we also have considered the beam again. Again, for the slope deflection that we are studying here, there is going to have no axial deformation. So zeta sub B is 0, delta sub B is 0, and delta sub A is 0. Only zeta sub A is going to be the degree of freedom. Okay. For this one, this is statically determinate because this is pin and this is roller. Okay. This problem going to have a lot of degree of freedom. Okay. The delta sub A is 0. You have zeta sub A. The delta sub B is 0. You still have zeta sub B. Over here you have both. So this have 4 degree of indeterminacy. Okay. For the frame. The frame under the application force, this one will move to this one. There is no axial deformation. So the delta sub by is 0. Okay. The delta sub b is going to occur due to the sideway, not to do the deformation. The same thing occur over here, the delta sub c, and delta sub cy is 0. And since the beam BC has no axial deformation, you will get the zeta sub b equal to zeta sub c. So this one, you will get delta sub b equal to delta sub c equal to delta, and you get the zeta sub b, and you get the zeta sub b. That are 3 degrees of freedom for this one. Okay. Then you guys go back and try to review this kind of thing. It's require you guys to use in the examination. Now, come to the slope deflection. By the slope deflection, we consider the continuous beam. That means the beam that's going to has a lot, and sorry, this is not a linear, a lot of support, okay? And then you just select a portion of the beam. For example, if this one, you may select this one as the A and this one as the B, and then you make assumption that the portion of this beam has the settlement. Okay, this means you're going to have this one for the delta, and then you just consider this frame that's subjected to uniformly distributed load. Okay, this is going to call the external load and point load over here. Now, under the settlement, and also plus under the load. Okay, that's we just provide the structure will deform. The structure will deform. Let's say if this one will deform somehow like this, okay, it's going to follow what we have. We have what? We have the zeta sub A over here. That means we have this one for the zeta sub A. And we also have this one, the slope, okay, with respect to the horizontal line is going to be zeta sub b here, okay? And then if you consider the settlement delta here, okay, the settlement delta here will make the beam have the chord like this. This is the chord, okay? And this is going to rotate, the chord going to be rotate based upon the horizontal line like this, okay? And that is going to call the phi equal to delta. Oh, sorry, I want it's going to involve with the something over here. It's going to have the phi. That is going to be the delta over L. Okay. All of this slope and phi when rotate clockwise is positive. Okay. And then you can see the shape of structure change. The shape of structure change, you will have the moment. Okay. The moment that's rotate clockwise, this is M sub AB because it occurred A, another N and B. And the moment here is going to be M sub BA. That's all things that's going to occur on the segment of the structure. Okay, it includes M sub AB and M sub BA. And it also has the deformation of theta sub A, theta sub B, and delta, and then all of this bending, all of this elastic curve is due to the bending moment only. Okay, there is no deformation due to shear, due to axial load, and it's going to have no axial deformation. It may have axial force, but there is no axial deformation. And then the joint is rigid, as I said. When the joint is rigid, again, the slope that occur on the left hand side and occur on the right hand side is going to be equal. That is the important thing about the rigid joint. Now, I just mentioned about this. All of rotation that occur clockwise, all of this moment, slope, and delta OL, okay, they are positive. And then we separate the consideration of this in four parts. One is due to theta sub A, one is due to theta sub B, one is due to delta, and one is due to the external load. And then you may go back to the equation that we has mentioned about KIT, okay, from the previous slide, okay. Just go back to this one. We have the equation over here. The equation over here is so messed up. Just go back to our conclusion that we have previously from our consideration. Okay, there are moments, end moment. Let's see. This is called the end moments. This called the end. The full name going to be end bending moment. We just left the bending and just call it end moment. This is due to theta sub A. Okay, this is due to theta sub A. Another one is due to theta sub B. Okay, you may go to what we have from the previous slide. And then another one is go to the delta. I will mention this later from the fixed end moment table. This is come from when you fix, okay, the two part of this, and you let one of the portion on the right has the settlement and the deflection of the beam is like this, and the moment occur here is going to be M sub AB. And the moment that occur here due to this kind of elastic curve, you may have this one bend like this, see? And this one is going to be M sub BA. And the equation is going to be minus 6 EI over L divided by L square delta. This is going to be the fixed end moment for this statement. Okay, and we will use that fixed end moment later. And the last part is due to the forces. That's going to be the fixed end moment that I just mentioned. So when you combine them together, M sub A, B are combined together. Okay, you will get the first equation with the fixed end moment AB. And if you combine them, M sub BA over here and BA over here together, you get this one. Okay, and please understand this. This is going to be E. E is going to be the modulus of elasticity. Okay, you guys, if we have the E for the steel, how much is this? You know that, right? Anyone? Let's go to sleep. If you have the I is what? The moment of inertia. If you have the section, that's B, this H is going to be BH cubed over 12. Okay, and then it's going to be in the form of millimeter power 4 or meter power 4. You know E, you know I. The L is going to be the length, okay? And then theta sub A, theta sub B, and the delta is the one that you know, okay? You known. And fixed end moment, also the one that you known. So from this equation actually is only the theta sub A and theta sub B. That is the unknown. And you call it degree of freedom. Okay? And we discussed this about last lecture. When we have the spatial beam, is have the fixed, let's say, support at the end of it. Okay. Let's see if we come to the beam that we just mentioned over here. Okay. The one that we mentioned has this end as the external pin or external roller. Okay, it's going to be spatial because the moment over here is going to be 0. Unlike this one, this is fixed. Okay, this is fixed. The moment here is not 0. So due to this spatial thing, okay, we come to what we have discussed when the beam has the spatial external roller. You got to consider the general form of this equation again. And then by doing this, you may see this is going to be the moment at B. Okay, this is M sub AB. And then this is going to be M sub BA. M sub BA as the roller point is going to be 0. So this one is going to be 0. So the second equation, you may put this one 0. And then when this is going to be the roller over here, the fixed end moment also BA equal to 0. So the term, this one is going to pass 0. So you have 0 here and 0 here. You can rearrange this one to get the term theta sub B. And then you put theta sub B back to the M sub AB. You got this spatial equation. The problem is you will not have a chance to know the slope theta sub B if you use this equation, but there is indirect way to compute the theta sub B later. Okay, this is important to know. Just come to our conclusion. That is general form of slope deflection equation. This is a spatial one. I will work on a problem, okay, the writing problem, by using this general form first. Last year, I make the examination basis upon only this set of equations. And from another previous year, most of the time it will be mixed. Okay. If I decide the problem, let's say, if the problem, just mention about it for the big picture of the problem that you guys supposed to have. If the problem be like this, okay, this kind of problem, every portion must use this one, okay, and then go to the one that's close to the picture of the beam from our experimental station. If another extreme, you have this problem, okay. This problem can be classified into 4 types, okay. If you cannot recall these 4 types, go back to my previous lecture, okay. You may have 4 types. One, if you like to find theta, let's say this is A, this is B, this is C, this is C. One find theta A, theta B, theta C, and theta D. The fourth, just like to find theta B and theta C. Okay, and the second, you like to find theta A, theta B, theta C. And the third, you like to find it just theta B, theta C, and theta D. They are not the same, okay? But for this problem on the top, okay, there is theta A is 0 for sure, theta D is 0. You are looking for theta B and theta C. So you just use this equation. Now, there are the mix, okay? I can decide the problem, okay, based upon one is going to be the roller, pin, roller, and fix, okay? This problem also be complicated, okay? Because under the application of the force, this one, and this one, when this force, this will have what? It will have theta sub A, theta sub B, and theta sub C. But theta sub D is 0. There is 3 degrees of freedom. The problem here can be separated into 1. We are looking for theta A, theta B, theta C. And then the next one, you may consider just the next one too. Consider only theta B and theta C. This kind of problem can be 2 types, okay? And then analogy to this one, you may have the beam, the big picture, okay? I didn't talk this with the Tyson yet. I will talk to them later. This is going to be fixed, and this is going to be pin, roller. This is going to similar to the purple one. Okay, this is the big picture that you may have for the slope deflection of the beam. So you must use your ending set. You must use your ending adjustment to work on this consideration. And this is going to be the first step that you guys must work on it. And then you will know the set of degree of freedom that you are going to work on it. And the fixed end moment will follow it. Okay? Because the fixed end moment from this set is different from this one. Okay, this is a fixed end moment of 2 sets. On this one, it will follow this side. Okay, for this one, special one, it follow on this side. And some of this one, you guys must remember it. For example, this is a simple. This also simple. Since the beam is symmetry, the fixed end moment is going to be the same. The fixed end moment is going to be the same. Please, this one, you're supposed to remember it. But for the one like this, I will provide you with the examination. Okay, that is what we supposed to do. And then for the light, that is for special one. Okay, the equation supposed to be also very simple. But for the long one like this, I will provide to you. And I ask you guys to remember the red. Okay, the red, the red circle. Okay, and for the other, okay, and this one, I will provide you if we have this one, okay, I will provide you. But for this one, you can remember it very easy. If you remember M sub AB equal to 2EI over L, if this one is A, 2 theta sub A plus theta sub B minus 3 delta over L plus fixed end moment AB. Following this, you may see we don't have the load over here. So this is 0. This is fixed. This is fixed. This one is 0. This one is 0. So now you have M sub AB equal to 2EI over L times minus 3 delta over L. By doing this, you get this one to be equal to minus 6EI matrix EI delta over L square. is going to be the moment over here, and it's rotate counterclockwise. That means it's going to be negative. Okay, you can do the same for m sub BA. The m sub BA is equal to 2ei over L, 2 theta B 0 plus theta A 0 minus 3 delta over L plus fixed end moment BA or 0. You will get the same result. Okay, for this one, minus 6ei delta divided by L squared over here, because this one also the counterclockwise movement. Okay, and you can use the special case of the equation and prove this one also. Okay, so please, you're supposed to remember this fixed equation. Okay, now most of the time we will start with consider the structure that I just mentioned to you. This is the important step, because you're going to select the set of the slope deflection equation, and it's going to be careful. Okay, be very careful to select this, and then just find the fixed end moment that's corresponding to the slope deflection equation. You just pick and then just put everything into the slope deflection equation of each member. One member, okay, typically has 2m. Okay, it's going to be m sub AB and m sub BA, and then you use the equation of equilibrium, okay, to set up the equation. The moment at a joint or at the node that we have mentioned must be in equilibrium. So you use the one you have for the step 3 and write the equation of equilibrium. Just a little bit, go back to what we have discussed before. Remember, we have this in where? We discussed this, supposed to be, no, not here. Okay, maybe here, right? Yeah, we have discussed about this portion. The moment that occur at the joint. Okay, if you come over here, you may put this one and just zoom it a little bit. There, we're talking about the moment at the joint. Okay, at the joint, and then we set the moment m at joint B, m sub BA plus m sub BC and m sub summation of moment at C. Okay, and go back to what we have discussed. Okay, and that is going to be the fourth step. And after you solve of this, you will solve the simultaneous equation. You will have the degree of freedom. Okay, and then you got to put this degree of freedom back into this equation. You will get the end moment. From the end moment, draw the free body diagram, and then you draw the shear diagram, and then you draw the moment diagram, you draw the elastic curve. Okay, now we finish our PowerPoint. We come to the extra example that we have. Okay, you guys can see it, right? Let's come to the problem. So have some fresh coffee and time to understand what I'm going to work on this problem here. Okay, and I hope you guys will follow me. If you can understand me, you are half done. Okay, so let us start by considering this beam. When we consider this beam, what we have, the beam has the fixed support at A and D. Okay, as A and D. And then what do we have? It's not very clear on this. What do we have over here? No, this is better, right? What do we have here is what? is going to be the beam that has, let me turn on the light over here. It may help us a little bit. Okay, that's help. That's help. Okay. Come to this. And then you got to first start by considering this. The problem has what? Has the fix at A and D. So what is the degree of indeterminacy of this one? For sure, you're going to have this one, this one, this one. That is going to be the reaction of the fixed support. And this one, this one, this one. Okay, that's the total of 6. And this one and this one. That is going to be the 8. And then if you know the free body diagram, only one that's connect A, B, C, D, E together, you have 3 equations. That means what? This problem, you have 5 degree of indeterminacy. That means if you solve this one by the force method, you will find 5 unknown force. That is going to be very big problem, unknown redundant. Okay, unknown redundant. It's going to be big problem. And again, coming to this, if you determine the degree of freedom of this problem, again, we're going to set up some assumption. Okay, based on this, the first one, the assumption of this, the material has the elastic, so I should call it linear elastic behavior, okay, of material under the forces. And then the second, the structure must have small deformation. Since we're talking about the degree of freedom, talking about the deformation. Okay, we got to set this one. And then also for the beam, we're going to set no axial deformation. Okay, and small deformation occur only due to the moment. By doing this, we will consider the degree of freedom clearer. So the theta sub A is 0, the delta sub A is 0, theta sub E is 0, and delta sub E is 0. Okay, also we have delta sub B is 0, delta sub C is 0. So there is going to be only the theta sub B, and also over here theta sub C. So you have only 2. So this problem can be solved by the displacement method, and it's going to be more effective than using the force method here. Okay, so next we come to determine the what's so-called the fixed end moment. Since the equation that we are looking for, they are all in the form of general equation. Since there is no external roller and pin. Okay, we use the general form of equation of slope deflection. Okay, use general form of slope deflection. And then what is mean? The fixed end moment will follow that. All of the beam will have the fixed end moment with this one fix. Okay, and then you go to the table. If you cannot remember it, this portion of the beam is subjected to uniformly distributed load of what? 20 kilonewton per meter and this one also 20 kilonewton per meter, and this one at the middle of 60 kilonewton. This is 4 meter, 4 meter. This is 8 meter. This is 8 meter. And then let me zoom it in. You will get the fixed end moment based on this. If you may recall from this one, and then you put the load at the middle, the defection of the beam going to be like this, and then the fixed end moment will follow this direction. This is fixed end moment A, B, and this is going to be fixed end moment BA. Okay, and you will have this one going to be the fixed end moment BC. This is B. This is going to be the fixed end moment CB. And the last one, that's going to be this is going to be fixed end moment. This is C, CE. This is E. This is going to be fixed end moment EC. And I should mention something. Since the force is symmetry, the fixed end moment here is equal. Fixed end moment here is equal. Fixed end moment here, they are going to be equal. But the direction is different. So it's going to have the positive and negative side. So when you put into the slope deflection equation, just be very careful about it. Okay, this is going to be WL squared from the table over 12, and it's going to be 20, and then times 8 squared, and then divided by 12. And then you got this one for 106.667 kilonewton meter. And if you take a look at this, you're going to get this one for 106.667 kilonewton meter also. They are the same. Okay. And the last one that we have, this one going to be, if you open the table, this is going to be PL over 8. P is 60. And then L is going to be 8, and then it's going to be divided by 8. So the result is going to be 60 kilonewton meter for this. Okay, now you are ready. It's going to be in the form of general form. Okay, we're going to use the 2EI over L for this problem. So let us start by M sub AB and M sub BA. The moment that we call the end moment following the slope deflection equation for this member is AB. Okay, this member also subjected to what we have is over here, the load over here, and then what we have, let me just put this one, only the end moment. This one going to be M sub AB, and this one going to be M sub BA, and it's going to rotate clockwise. Always clockwise is positive. So next, this is going to be M sub BC, and this is going to be M sub CB. Okay, they are different. And then this is going to be M sub CE. And this is going to be M sub EC. All of them will follow the general form of this equation, M sub AB equal to 2. And EI is constant. If you go above it, E is going to be like this. That is going to be 20, 10 minus 6 kilonewton per square meter. And this one, since we use in meter, this one going to be 1010 minus 6 meter powerful, and we're going to use 2 EI. So the EI is going to be 20, 10 power 6, 1010 minus 6. So cut. That is going to be 20,000. And then unit is going to be kilonewton
per square meter times meter power 4. So it's going to be kilonewton meter square. Okay, we just put it here and then divided by 8. Okay, let me move a little bit. Divided by 8, and then over here we have 2 theta A plus theta B minus 3 delta over L. Okay, and then we have the plus fixed end moment AB. Fixed end moment AB is over here. Is counterclockwise. Is going to be not plus, minus 106.667. And what we have over here, the theta at A is fixed. Okay, so this term is 0. This term is 0. And we have the theta sub B, because theta sub B is the unknown we are looking for. And what is the delta? The delta is the settlement. Okay, B has no settlement. Okay, the problem said there is the downward settlement, vertical downward settlement, but it occur at C, not B. Okay, based on this, so an answer 0 is going to be this term. Just cut it, and then the equation can be very simple. Equal to 2/8. That is going to be EI over 4 theta sub B and minus 106.667. That is going to be M sub AB. Next, M sub BA is going to be 2 EI over 8 and 2 theta B plus 0 theta A minus 0. Okay, and then over here, this is fixed end moment BA. Fixed end moment BA is positive, plus 106.667. Now, this is 4 over 8. This is EI over 2 theta B and plus 106.667. Okay, then we come to the M sub BC. M sub BC is over here. Okay, and this problem is going to be involved with the settlement occur over here. And let me put in this direction. This settlement going provide the chord in this direction. Okay, so M sub BC is going to be, let me be very careful on this. It's going to be 2 EI over 8 and 2 theta B, and plus theta C and minus 3, and then it's going to have the term delta over L. Okay, let me put this. And then we have this one is the rotation. So this is going to be the angle phi. Okay, the phi in this one is clockwise, so it's going to be the positive of this one is 25 millimeter and divided by the length of 8,000 millimeter. If you put them into the calculator, that is going to be 1 over 320. So put this one 1 over 320. And don't forget, that's going to time the delta over L, right? So then you compute. This is delta over L. It's going to have EI. Okay, later we will. So this is going to be counterclockwise, minus 106.667. And then if you put this one together, this is going to be 4 EI over L, that theta sub B. So EI over 2 theta sub B. 2 EI over 8 theta sub C plus EI over 4 theta sub C. Now, this portion, you must time EI. that is going to be 20,000 times 3 divided by 320. Okay. And then you got to minus 106.667. So this one later, after compute in your calculator, you're going to get 153.542. The unit going to be in kilonewton meter later. Okay. And then we got to go faster. CB, that is going to be 2EI over 8, 2 theta C plus theta B minus 3. Now, on this one, you got to use this angle of phi, and then you minus the same is going to be clockwise positive. That is going to be 1 over 320. And then you use this one. This is going to be positive plus 106.667. So this one going to be EI theta sub B. Theta C first. EI over 2 for EI theta C over 8. EI over 2 theta sub C plus EI over 4 theta sub B. And then you times this one. It's going to minus and plus here. Okay, when you have this one, it's going to be 59.792 plus 59.792. And then the last step over here. And for the last step, you also have this kind of chord rotation. Okay, and it's going to be over here, M sub CE, M sub CE 2EI over 8. 2 theta sub C plus theta sub E. If you recall, this is Defection. This is Defection. Theta sub C is 0. Okay. And then it's going to be minus 3. This one. Rotation here is counterclockwise. So it's going to be minus 1 over 320. Okay. And then close this up. And this is counterclockwise minus value is over here is 60. Value 60. Just put it 60. And then you get this one to be 4 EI theta sub C over 8. EI theta sub C over 2. And this is 0, right? Okay. And then you just times this one going to be positive and minus 60. That is going to be minus 13.125. And the last one, M sub EC, is going to be 2EI over L. And then it's going to be 0 to theta E. And then plus theta C minus 3. The same minus 1 over 320. And this is minus. Okay. And parenthesis. And then this one is going to be the fixed end moment of plus 60. So you get this one divided by 4. Okay, theta sub C. And this one going to be plus what? 106.875. 106.875. Now you have all the moment. But next, you got to consider the point here is going to be the B. The point here is going to be the C. You are going to consider the equation of equilibrium that is going to use to solve for theta sub B. That means you're going to use this one. And so for the theta sub C, you're going to use this one. So M sub BA. This is going to be third law of Newton. M sub BA. And M sub BC is going to be this one. M sub BC. The summation of these two moments must be 0. And this one, M sub CB, M sub CB. And the black one, M sub CE. This is M sub CE. We use the first one, summation of the moment at B is 0. And you can see this is counterclockwise. So you have M sub BA bwak M sub BA บวก plus sorry Sorry, in Thai, BC and combination of them gonna be 0. Another one is going to be summation of the moment of C is 0, and this one you have M sub C B and plus N sub C E, and combination of them gonna be 0. You're going to work concrete, okay? Just combine them. This is going to be EI theta B minus 2 BA, and then plus 106.667, and then you have this one, okay? You just plus EI divided by 2 theta sub B plus EI divided by 4 theta sub C minus 153.542, and this is gonna be equal to 0. You're going to get this one for the first equation for EI theta sub B. Sorry, I put this one down. Sorry. Okay. And then just plus EI theta sub C, and this is going to be equal 187.5. You got to stop video and trying to solve it by yourself. Then you got to use these two equations combined together. This one EI divided by 2 theta sub C plus EI divided for theta sub B plus 59.792, and then not enough, you have this one plus EI divided by 2 theta sub C minus 13.125, and then equal to 0. You get the second equation EI theta sub B plus 4 EI theta sub C, and then you get this one equal to I don't think that's correct. Okay, that is going to be minus of these two is going to be 46.667 times this one times this one 4 and 4 times this. Okay, I understand this. This is move the 4. That is going to be 186.608. 186.608. That is going to be the number 2. Now you solve these two equations, you will get theta sub B. Use your calculator. Okay, EI theta sub B equal to 62.445 and positive clockwise, and then EI theta C, you get this one for minus 62.278, or it's going to be equal to 62.278 is going to be counterclockwise. Now you got to put this one back into this whole equation that you have, okay, and then you get the end moment. Let me say you get the end moment M sub AB equal to minus 91.056 kilonewton meter, and M sub BA is going to be 137.89 kilonewton meter. Just put it back, okay, into these two equations. For the blue, okay, so the blue, just get the M sub BC, 137.81 kilonewton meter. It will follow this. These two must be equal. If not equal, it's wrong. If it's close to each other, just sum and divide it by 2 to average it, okay, and then M sub CB, okay, you put it into M sub CB. M sub CB is over here. You will get it 44.264 kilonewton meter, and you will get M sub CE is going to be minus 44.264 kilonewton meter. they must be equal following this condition and ends up EC. And then you will get this one for 91.306 kilonewton meter. Let me put all of this into the free body diagram in order us to show this. This is 91.306. That is clockwise. Okay, 91.306 kilonewton meter. Just left the unit first. And then this one is minus. That minus is counterclockwise. That is 44.264. And then this is going to be 44.264. And then what we have is 91.0. This is negative, right? This is negative. Counterclockwise, 91.056. And then this one is positive. You get this one 137.81. Okay. And then you get this one also. Okay. This one is what? This one is negative. Negative. Okay. It's going to be counterclockwise. And then before you can use this free body diagram, it's going to be step 5, draw free body diagram. Okay, and V diagram, and moment diagram, and elastic curve. Okay, my writing is not good, but believe me, we don't have much time on this. And then you got to determine the shear force that occur over here. Let me put this one. Okay, we don't have much time on this. And looking for my pencil. Okay, over here. Let's say we're going to have the force here. Okay, that is going to be V sub A, and this is going to be V sub B, and this beam is subjected to the 20 kilonewton per meter. You are looking for what? You are looking for the shear force. So summation of the moment about A is 0. Okay, V sub B rotates like this is positive. You have V sub B, and your V sub B rotates like this, positive V sub B times 8. Okay, that is going to be rotated in this way, and then it's going to plus 91.056 is going to be in the same rotation. Okay, and then you have this one. This one is the total 20 times 8. That is going to be 160. And this 160 is going to time 4 meters here. And then we have plus 160 times 4. And then, no, it's not plus, right? This is going to be the minus. It's minus. And then you're going to minus 137. Okay, 0.89. This is 0.89 equal to 0. You put everything into your calculator. You will get V sub B equal to 85.854 kilonewton. And then you have the summation of F sub Y equal to 0. You have V sub A. And then V sub B is plus 85.854. This is equal to 85.854 kilonewton. And then you have equal to 160. So your V sub A over here is going to be 74.146 kilonewton. This is going to be 74.146 kilonewton. And then you got to work on the author. Let's see. You have the shear over here. You have the shear over here. And the shear over here. And the shear over here. What the value that I have 35.88. This is 35.88. And this is 24.14, if I'm correct. Yeah. No, 24.12, 24.12 kilonewton, and this is kilonewton. And inside 68.297, this is going to be 68.297 kilonewton. And another one is 80. It's very hard to find it. I get it what? 96.703. This is going to be 96.703. Okay, kilonewton. And then we still have about 10 minutes. This is going to be X meter. And let's check. This is V kilonewton. We have what? 74.14 scale. 100 kilonewton per 10 millimeter. So this is going to be 7 something. Up. Okay. Plus 74.146. And then you have dV by dx equal to minus 20. This is going to be downward. And this is going to be 85.854 upward. Okay. This is going to be 85.854 upward. So you have the shape of shear diagram like this. And then you can determine this length. Just divide 74 by this one. You may got this one about 3.7 meter. Okay. And then next, this is 93.703. This is going to be up. Okay. 91.703. And then this is 68.297, just up. Okay, minus 68.297. And then you get this, and this is the point of zero shear. And then you get this one for just divide 91.703 by slope. dV by dx equal to minus 20. And if you like to show, this is minus 20. And this is going to be minus 20. And you get this one for 4.59. Okay, just have given 4.59 meter. And the last one, 24.12. That is going to be very small. 24 plus 24.12. And then you don't have this one dV by dx equal to 0. Okay, and then for this one you get the downward for 60. It's going to be minus 60 plus 24.12. You get this one equal to this one 35.88. It's going to be minus. Okay, and then you push this one 35.8 will push this one up. Okay, that's the shear diagram. For the moment diagram, this is X meter, and this is going to be moment kilonewton meter. And then you guys has the 191.056 again, 100 kilonewton meter per 10 millimeter. This is negative. Okay, this is going to be minus 91.056. Okay, and then a little bit further, you have this one, okay, of slope. This one dm by dx equal to positive 74.146. And for sure, this one will up. And since this one is 0, the dm by dx equal to 0 over here. And the moment over here, m over here, minus 91.056, and then it's going to be equal to the area here, 1/2 of 3.7. Let's check this one for me, and have 74.146. Okay, if you push everything in your calculator, your m is going to be 46.46 46.134. So this is about 4 point something millimeter. So your curve is going to be something like this, and make sure this is going to be your correct slope. Okay, and then this is 37. Sure, this is going to be the negative moment for this, just like this one, minus 137. Okay, 37 point 0.89, and then you have this one for the shear over here. Okay, of 85. This is minus 85.854. So the slope here, the dm by dx is going to be minus 85.854, and then the curve is going to be something like this, and then this is going to be the curve on this side. The dm by dx is going to be positive 91.703, and then this is going to be upward. You do the same computation like this, you will get this one 72.568. Okay, this is going to be 72.568. Do the same calculation at this. Okay, and then the curve going to be upward like this, and this dm by dx equal to 0, and then this is going to be curve downward. Okay, and then you will have this one to be the slope dm by dx equal to minus 68. Okay, 0.297, and the value of the moment is going to be this one, 44. That means I put it too much. Actually, it's supposed to be about this, and then the curve must be this one. Okay, and let me emphasize this one is going to be the slope, and this one is going to be 44.264. Now, this is Python. Okay, the curve here must be something like this, and since this one 24.12 dm by dx is going to be plus 24.12. Okay, and the moment here, when here, m here, minus this one, minus of 24. This one is incorrect, right? How come? It's 44. This is minus of 44.264, and then it's going to be equal to this area, 4 times 24.12, and then if you push it, you will get moment here equal to 52.216, and finally what we have is the moment here of 91.306 is going to be negative. So this one is minus 91.306, and then you have the curve here, and then you have the dm by dx equal to what? Equal to this one, minus 35.87. Okay, everybody, a lot of people said, oh, this is so messed up. No, usually if you put it into one page, okay, when you reference it later, it's going to be easier, and you have no choice. Okay, if you like to have it clearer, you go to the PowerPoint. Okay, things gonna get clearer. This is going to be the elastic curve. Now this is fixed. This is concave downward. This is concave upward. Okay, and this is concave downward. Okay, and this is concave upward. Let's say this is concave upward, and then this is concave downward. Let's me concave downward. Okay, and then this is gonna concave upward. And then finally, you have this one. This one is downward. You have this one is downward. This one going to be some. This is going to be the elastic curve of this one. And then finally, what we have for the reinforcement, you got to follow the rules that we has mentioned. Okay, for this one, negative moment, put the slope from the reinforcement on the top. For this one, positive, put it on the bottom. This one, put it on the top. And this one, put it on the bottom. For this one, put it on the top. And this one, put it on the bottom. And then put it on the top. Okay, that is going to be the placement of the steel reinforcement. So we end up at 3 o'clock. Okay, so you guys can move to your next class. Okay, today we finish our first important problem and review everything. Next